And in order to create nParticles, we can do that a number of ways, but the most common is to create an emitter. So I'm going to come down to nParticles, create nParticles, and then create emitter. Now before I do that, there are a number of presets that can be selected underneath. And this kind of sets up a bunch of different attributes for the particle type. So I'm going to set this to balls to start off with, and then I'm going to go to the options for creating the emitter. Something that we talked about a little bit before was the idea of the Nucleus Solver. And the Nucleus Solver is a system that calculates dynamic interactions in Maya. And there is, the Nucleus Solver handles hair, it handles cloth, it handles particles, and all of these sort of, all these systems can sort of interact and work together. And so that's what it means when it says create new solver. You can create just basically one solver for your entire scene, and that'll ensure that all of your particles are interacting with each other. So I'm going to call this my particle emitter. There's different types of emitters. I'm going to leave this at omni. There's a rate that we can change after the fact, speed, but I'm just going to hit create. Okay. Now before I hit play, there's a couple of things I want to do. I want to go into the animation settings and make sure that my playback speed is set on play every frame. And that's to make sure that the dynamics calculations happen by comparing the previous frame to some new information to generate the current frame. And so if you don't have it set to play every frame, then you're going to be skipping frames and the calculations won't be able to keep up, and you're going to generate improper simulations. So set play every frame, and then set the max playback speed to real time. And in fact, I'm going to go to, I think it's under the settings, and I want to set the time to 30 frames per second because that's what our animation is going to happen at. So 30 frames per second, and then under the time slider, real time, 30 frames per second as the max playback speed. So it won't go faster than that, but chances are it'll go slower than that in order to give it time to calculate everything. And I'm also going to give myself lots of time in the time slider. So I'm going to set this start range from 1. For whatever reason, when it converted 24 frames per second to 30 frames per second, it gave me a 1.25 partial frame. So I'm going to set that to 1. And then maybe 1,000 for our full time slider. So we have lots of time to see the particles reacting in the scene. Now, when I scrub, you'll notice this error here, this warning, nucleus evaluation skipped, frame change too large. And again, that's what I was talking about with playing every frame. If you're rewinding or scrubbing backwards in the timeline, you're not going to get results. And if you scrub forward, you're going to get weird, erratic results. So it's important to just rewind back to the beginning and then hit play. Okay, so we've got our emitter throwing these ball particles into the scene, and I'm just going to turn off the grid so that we can see this a little bit clearer. I'm also going to move the emitter up in our scene so we've got a little bit more room to see it. So you can see a few things happening here. So we've got these particles being emitted. They're spheres. They've been colorized sort of randomly between red, purple, and blue. And they're also falling down. And the reason that they're falling down is because the Nucleus Solver has gravity by default on it. And so let's just take a look in the outliner here. We've got my particle emitter. We've got this nParticle, which is actually the particles themselves. And in order to control its attributes, we're going to be looking at this nParticle shape node quite a lot. And then there's this nucleus node. And again, this is kind of the master sort of calculator for the scene. Most of these attributes you don't really need to change. You can see there's gravity here at 9.8, which means 9.8 meters per second squared, which is the force of, the sort of regular force of gravity on Earth here. You can change that, but I would advise against changing it unless you're working with a sort of non-real world scenario. And in fact, you might, it's true that sort of these microscopic environments don't really respond to gravity in this sort of typical way. You know, the molecules aren't falling to the bottom of the cell, wherever that is, at a quick rate. So instead of dropping this gravity to 0, usually what I do is just leave that as is, leave the gravity direction as is, but I go to my nParticle shape, and then under dynamic properties we have an attribute called ignore solver gravity and ignore solver wind. And wind by default is off in the Nucleus Solver, but you can set up wind so things are sort of blown around. But basically, if we set ignore, then these things are going to behave as though they're in a gravity-free environment, and they're kind of weightless. Okay, but for the time being, I'm gonna leave that on so that we've got these balls moving around a little bit more. Maya has a sort of a legacy dynamic system, and that can be found in this row of menus here. Particles, create emitter. It's kind of got all the same sort of attributes and sort of commands and tools, but you really, for most of the time, you really just need to worry about nParticles. Don't even really bother with the old system. The benefit of, one of the major benefits of this nParticle, besides being this kind of updated solver calculation system, is that the particles can actually collide with each other. And if we check under collisions, so there's lots of tabs in this particle shape node, and it can be easy to get lost. So I'll try to be clear about where we are. So under collisions, there are 2 checkboxes here. One is collide, and that's to collide with other things in the scene that are set up as colliders. And then there is self-collide, which means that the particles can bounce off of each other. And as you can see, there aren't really any particles that are sort of interpenetrating. So if I turn this off and played it back, now you can see that the particles are able to interpenetrate and they're not colliding with each other. So depending on your scene, you might want to make sure that that's on so that the particles actually respect each other's space. If you want to see what the collision, where the collisions are actually occurring, you can check this solver display to see the collision thickness or the self-collision thickness. And you might see them turn yellow, you might not, and we'll see why that might be. But basically, this is demonstrating a radius, and if we clip, we can see that that's the radius that the collision is being detected at. So if we turned up the self-collide width scale a little bit, maybe something like 1.2. Okay, so the collide width scale seems to be driving this, even though we've set it as self-collision. So the collide width scale, we can see, has a kind of a radius. And so if we set this collide width scale all the way up, then things would bounce off each other at a greater distance. And if we kind of look inside this, just by clipping it through, we can see that the particle itself is kind of sitting inside that. So if you want the particles to bounce off each other at the same radius that the particles themselves are, then you can leave these at 1. There are some other attributes like bounce, friction, and stickiness that we can look at a bit later that will define, you know, how the particles actually react when they collide with each other. So I think what we might do just for fun is to create a kind of sort of filling a box type thing. So I'm going to create a cube, and I'm going to delete the front and the top faces and scale this up quite a lot so that we kind of have this sort of tall box container-like thing. And in order to either we could reverse the normals so that the normals face the inside because the collisions need to happen against the normal direction. Or what we could do is we could just go to Edit Mesh, Extrude, and give it a bit of thickness, maybe 0.1, maybe a little bit more, 0.3. And then we've got sort of a box with some thickness. So if we rewind and play, you'll notice that the particles just pass right through it. And that's because by default, not everything in the scene is set up to collide with things. In order to do that, we need to select our object and go down under nMesh, create passive collider. And the only real option in this make collide option is to make sure that the solver is the one that is connected to the rest of the stuff in the scene. So Nucleus 1 is connected to our particles, so we want to make sure that that's the same solver that is connected to our collider. And now there's an nRigid node that's been created, and if we rewind and play, now we've got the balls colliding with the box. So as I was saying, the nRigid node has a lot of the same attributes that the particle shape does, especially in this collide tab. So we can turn the collide off and on. We can change the thickness, and what the thickness, if we kind of look just very carefully, you can see that these particles are not actually sitting exactly on the mesh itself. There's a little bit of a gap in there, and that's the same thing that I was talking about with the collision radius. And so if we turn on that display, then we can see that that's sort of adding a little bit of thickness. And so we could turn this down, but we don't want to turn it down all the way to 0 because that'll create problems with the calculation, and sometimes particles might go through, just kind of pass right through, especially if particles are traveling very, very quickly. So if in your own scenes you have issues where particles are passing through geometry that it should be colliding with, either you can turn up the collision thickness a little bit to make sure that it's detecting that, or you can go into the nucleus and turn up some of these sub-steps and max collision iterations to kind of refine the preciseness of the calculation, although that will increase the amount of time it takes to actually solve the simulation. So that's just something to keep in mind. But for now, because we're looking at this from a medium distance, that tiny little gap really doesn't bother us. So the illusion of the collision is perfectly adequate. Okay. So there's some other attributes with these particles that we can play with to change the look. There are a number of different ways that particles can be shaded, and so we'll take a look at some of these. This is set to blobby surface, but let's look at some of the other types. So there are points, and these will render just as points. You can increase the point size, but it's basically just a little square. There is multi-points, and that's like points except that there's a cluster of them together, and so you can change the number of the points that are rendered together. But if we sort of step through the frames, you can kind of see here that these clusters are moving together. So it's to create the illusion of more particles than there actually are. There are streaks, and these kind of have these little line effect that kind of fades out, and I believe the streaks are longer depending on the faster they go. Likewise, there's multi-streaks, which are like streaks except there's a bunch of them together. Then there's numeric, and numeric might seem weird But the numeric rendering style is really actually useful to give you diagnostic information about the particles in your scene. So right now the attribute that it's looking at is the particle ID. And so if you're having problems with individual particles, you can say, okay, well, this is particle 314, and you can access the particle ID. And we could even go out here and try to find particle number 1. I don't know where it is, but you could also change a different attribute. You could set the age, or sort of look at the age in terms of this numerical display. And so the ones right close to the emitter have a very low age, and the ones out here have a long age. And this will help you when you're setting things like ramps to change. Like if you wanted to change the color of the particle as it aged, then this would give you a really clear indication of, say, I want the particles to be blue by the time they get down here, and I want them to be red when they're born. Then we could say red for a value of 0 and blue for a value of, let's see, maybe 1.7. I think that's kind of the lowest that's down here. 1.5 maybe 2. And so you can really easily figure out the data that you want. So that's the value of the numeric render type. And then when you're actually rendering it, you'll change it to something like spheres. And spheres are spheres. There are a few others, but we'll leave these as spheres for the time being. So this is all in the shading tab, and we can change the opacity, and the color, and the incandescence. And this is where I was talking about how the particles, the material of particles is a little bit strange, because there's two sort of places that particle materials live. And if we look at the hyper shade under the rendering editor, we've got these two materials, one called nPballs blend and nPballs volume. And this is just to illustrate. I'm not going to talk much about this because there's some fairly complex connections between materials and the particles themselves. You can see that there's, if I graph this, you can see that there's kind of a complex relationship between the particles. So all of that to say that when you want to change the appearance of materials, usually it's the best idea, the simplest, to change the color and the opacity and the incandescence and everything in the actual particle shape node. So if we wanted to, like that example that we were looking at, we could change the age, the color input, to be the age. And that means that it's coloring the particles depending on how old they are. And this is the ramp that we set here. So we can set it to be red at a value of 0. And blue, we want it to be, let's see if we can do 2. So now when the particles get to an age of 2, and that means 2 seconds, so at frame 60 is when they should start turning blue. Let's see if that happens at frame 60. Yeah. So that's how you can, and by default it's set to randomized ID. So let's just reset the ramp. It can be difficult to assign materials because they're driven in a specific way. I might talk about a little bit about that later because it's a little bit complex. Basically, what you can try for some things is, if you wanted to create like a surface shader or something like that, this isn't a subsurface scattering shader, but you can select the particles and then assign material to selection, and then it doesn't look like anything's changed, but let's see if we render them. Now they've got the surface shader applied to them, but it's kind of hard to see the connection because in the attribute editor you don't see that material being applied, and if you come down to the shading, you might get confused and start trying to change, you know, the coloring and stuff like that. But really, the shader is kind of still been applied in the background. So it's a little bit complicated, and I wouldn't necessarily, well, yeah, we can explore that a little bit later, but for now we'll continue with the kind of default particle attributes. So some of the sort of bounciness and stickiness that I mentioned, we can set the bounce up to 1, and then we can also come into the cube attributes and turn the bounce way up, and then we've really got a very bouncy simulation. Conversely, if we wanted to make it quite sticky, we could set the stickiness up, and then excuse me, then you can see that the particles are really sticking to the surface. So depending on what type of material or type of particle you're trying to simulate, you can play with that. But another nice thing about nParticles is that they can actually behave a little bit more like a liquid or a fluid. So there is a tab in here, I'm just going to collapse some of them, called Liquid Simulation. And liquid simulation changes a few properties that make it behave a little bit more like a fluid. They make it the particles incompressible, and that means that when they don't sort of pile up and stack in the same way. And it might be a little bit hard to see this, but if you're wanting to simulate a fluid, then liquid simulation can help you get a little bit more accuracy. And the viscosity will also help things kind of stick together. There's also surface tension, which will help the particles kind of group together in a more believable way. But you'll notice that the particles themselves are they're still individual. And in order to get a sort of cohesive mesh over it, we can actually go modify, convert nParticle to polygons. And that's going to take, similar to how molecular Maya creates a mesh around the particles, this kind of does the same thing. And so we've got this kind of mesh being generated with the particles. But you'll notice that there's no mesh sort of in between, and that's because the particles are too far apart from each other. So we would have to change some of the output mesh settings. Again, this output mesh is in the particle shape, under the particle shape, and this is where we can change how the particles are creating the mesh around them. So we could increase the blobby radius, and that kind of gives a larger scale to the particles so that they kind of clump together a bit more. We could also increase the mesh triangle size, and the mesh triangle size, as you might expect, is sort of how large the triangles are, and it kind of smooths out the result. So if it's kind of too defined, you can increase that. And then the threshold, if we reduce that, is how close the particles need to be together in order to have the mesh sort of bridging the gap between them. So we can kind of create this look, and you might want to, you can play with that sort of thing. There's different output mesh types. You can have triangles, you can also have quads, which looks a little bit blocky by default, but you can increase the smoothing. So we could put this up to something like 20, and then you've kind of got a little bit of a smoother sort of mesh. Or with triangles, you can increase the smoothing and get kind of a result like that. You can get problems where the mesh has holes in it and isn't completely filled, and that's going to create problems obviously when you're rendering and trying to create your final output. So you might have to bring down the mesh triangle size, and I wonder if play with some of the other settings. 8 to kind of reduce the number of holes. you'll notice that this poly surface 1 has been created, and that's your output mesh. So you could call this your output liquid. And this is the actual geometry of it, as you'll realize, is being driven by the particle shapes themselves. So you don't want to be coming in here, selecting a face, and trying to manipulate the geometry there, because as soon as you rewind, that information is going to be sort of overridden, and it's going to screw things up. So you don't want to be changing the mesh itself. If you did want to, if you just wanted to have the particle mesh kind of at one state, and I'm just going to come back in here and increase a few of this a little bit so it's a little bit more full looking. If you just said, okay, I just kind of want this mesh here, what you can do is come into the node editor, which defines the connections between things, and you can see that we've got the nParticle shape information is being passed into polygon mesh. And if you hover over these arrows, you can actually see what that information is. And come on. Okay, I don't know why it's not showing, but we can also expand it and see the information. We can see that the output mesh is driving what the mesh is for this liquid shape. So really all we need to do is just delete that connection, and lo and behold, we've got a mesh that's no longer tied to the particles, and so it's just static now. Now that's probably not a great idea, because you might want to come back and change the simulation a little bit. So a better way might just be to duplicate the mesh, and now we've got a mesh that is independent of the particles and it retains its geometry. So again, in order to get the particles to this polygon, we went to Modify, Convert, nParticles to Polygons. And what that does is it also hides the particles themselves, but they're still there. And so if we select on this nParticle node and come down to the Object Display tab in the nParticle shape, this is a little bit counterintuitive, but if we uncheck Intermediate Object, then the particles should actually show up. And the reason that we can't see them, I believe, is because they're just hiding inside the mesh. So this particle size attribute, I don't know if I mentioned this before, but this will also define the particle size. So we can set this back to 0.2. But for example, if in our output mesh our threshold was too high, then we could see what, we could still see what the particles are doing and try to troubleshoot how we want the simulation to unfold. Anyway, so that's under Object Display Intermediate Object. It's useful to know about. So that's pretty much what I wanted to talk about as an introduction to sort of nParticles and liquid simulations and stuff like that. There are other dynamic properties such as drag and damp that can sort of create the illusion of something moving through thicker air or through water or some other thicker medium. You can turn down the conserve, which will reduce the amount of energy that's conserved in the simulation, and so things can really slow down when you have the conserve even down just a tiny little bit. And that's because energy is not being conserved in the simulation. And a little bit of drag also goes a long way, so that will definitely make things sluggish. But that might be what you're after, depending on what kind of output you're actually wanting to do.